So hello everyone, welcome back to another particular class of our organic spectroscopy course, and this is the class 6 of our IR spectroscopy, and formally this is the last lecture of our IR spectroscopy. So in our previous discussion, that is a class 5, we are talking about the hydrogen bonding and the inductive effects which actually affect the IR values. So if you are not seen that particular video and just directly come to this particular video, so I would highly suggest to go back and see the previous video. The link is I think here or here, the I button. So go first, check out that particular video, then come back here, because this particular video is the continuation of the previous video. And also I have put so much question regarding the IR value in the community tab, so do check out that particular question and solve accordingly. So now let's start our video. So in this particular video we're talking about the different factors affecting the IR values. So first we are talking about the electronegativity. So the electronegativity, it actually affects the IR spectra by influencing the bond polarity and the bond strength. That means if one atom is more electronegative, then what happened that it actually pulls the electron density towards itself, which increase the bond polarity, and this actually result in a stronger dipole moment, which actually enhance the IR absorption intensity. Similarly, when the electronegativity differs, then it actually increase the force constant, which leads to the higher vibrational frequency. For example, here this is a acetylene part. Now what happened that this actually have the most electronegativity. So what happened that the electron density between these two particular bond is actually shifted towards here. Like ideally if there is a two bond, the two covalent bond, so what happened, the electron density is lying in between that particular bond. But if one of the particular group is electronegative so much, so it actually drags this particular electron density towards its side. So for that particular example from here, we can understand that for this particular part, the electron density is nearly here, nearly the carbon side, because this particular carbon is electronegative. And due to the shift of this particular electron density towards carbon side, this particular bond becomes much more stronger, and which increase the force constant. And since it is increasing the force constant, that means the new value is also increasing, because the new bar is directly proportional to force constant. That's why here you can find here that this having the lower electronegativity, this have the moderate electronegativity, this is the highest electronegativity. That's why this CH bond vibration is much higher over this and this. Also, that S character and electronegativity have the same trend. Like here you can find here the S character here is a 50%, because it is a sp hybridization. Here you can find here the S character is 33%, and here is the 25%. So that means S character is also increasing. That means the uh, new bar value, that is the wave number, is also increasing. So I hope this will be clear for you. Now let us talking about the resonance. Now resonance, how the resonance actually influence the IR value. Like due to the resonance, the single bond gets, there is a one L is missing. Single bond gets partial double bond character, and the double bond gets partial single bond character. When a single bond gets partial double bond character, then force constant increases. Obviously, because if it is a partial double bond character observed, then the bond become much more stronger. That means the force constant increase, and obviously the new bar is also increasing. And when a double bond gets partial single bond character, then force constant decrease. Hence, new bar is also decrease. Also, another thing that you have to remember, that between inductive effect and resonance, always remember resonance effect has the higher priority over inductive effect. So this thing you have to remember very cautiously. Now here you can find that this is the free carbonyl group. This free carbonyl contains only the inductive effect group. Okay, but here, due to the presence of this particular alpha beta unsaturation, this can go here and this go here. So that means this particular carbonyl group is now having the partial single bond character. That means the new bond decrease because the force constant is decreasing here. So that's why the IR value of this particular is much greater than this. And if you talk about this particular CC bond uh, stretching frequency, then here the CC bond stretching frequency much higher because this particular bond getting the partial double bond characteristics. So you have to remember this particular thing. Now let us talk about the field effect. This is the very interesting effect that actually influence the IR value. So basically what happened, the field effect in IR spectroscopy refer to the influence of nearby charge or polar group on the electron density of a bond which altering its strength and vibrational frequency. Okay, so what happened that here this chlorine contains their own electron density, and also this particular carbonyl oxygen also have own electron density. Now since these two particular present in the closer proximity, so there is always a repulsion is observed. Now due to eliminate this particular repulsion, this present in the double bond form. Now if it is present in the single bond form, so what happened? Oh, this is present something like this, and Cl is also here. So Cl have their own electron density, or we can say the electron density, and also now since it is present in the single bond character, now the oxygen contains a negative charge. That means it has the more electron density, and due to this two electron density, since these two groups are in a closer proximity, so there is a heavy repulsion has been observed, and this is nothing but the field effect. So in this orientation, this negative charge can't present in the oxygen center. It should present in the double bond region, and that's why here in this particular case, this are actually dominates in the double bond characteristic. There's a carbonyl bond dominance. That means the force constant of this particular group is much higher, and which leads to the higher nu bar value or the higher wave numbers. However, here, if this is present in the O negative form also, then there is a no group is there to actually repulse that particular electron density, because the chlorine here in the axial bond, that means far away. That means here in this particular no field effect is observed. That means that this particular new CO is much lesser over this particular group. So increase electron density, that means the bond is stronger, that means the higher frequency. And also if there is a decreased electron density such as here, that means this particular carbonyl bond is now weaker, that means it will tend to the lower frequency. So I hope this is clear for you because this is a little bit tricky, but I hope that you will understand. Now let's talk about the ring size. This is also an important aspect where to determine the IR values. Like always remember, if there is a smaller ring, and in the case of all smaller ring, there is a ring strain is observed. And ring strain, you already know that angle strain, ring strain. If don't know, then you can check out the conformers lectures. Okay, so since the smaller ring contains the more ring strain, which leads to the particular this particular carbonyl bond is stronger and shorter, which result in the higher frequency or the blue shift in IR absorption. And if it is a larger ring, this particular rings having the lesser ring strain, and this particular lesser ring strain actually tends to make this particular carbonyl bond relax and weaker, and which leads to the lower frequency, or we can say the lower wave number in IR absorption. For example, here you can see this three particular structure is there, where this particular carbon for the 6-member ring, the exocyclic carbonyls, our value is the 1751, and this is the much higher ring strength, but not that much. That's why it is a little higher. But in the case of cyclobutane, cyclobutanone type of system, the new CO value is 1780. This is the much higher. So from here we can put a conclusion that the new CO is depend upon the 1 by bond angle and the directly proportional to the ring strain. Okay, so now let us do some examples over the ring strain. Here you can find that this is the 6-member ring, this is the 5-member ring, this is the 4-member ring. That means the new CO of this particular ring is much higher over this and over this. Although you can say that here is also a partial double bond or single bond characteristic has been observed due to resonance, but this phenomena is observed in both of 3 cases. Okay, and for this particular case also, there is a very lesser chance to do because of the ring strain. However, the trend is something like this. New CO is increasing. Similar type of concept has been applied in this type of exocyclic double bond CC double bond IR spectrum, where the ring strain actually give the actual explanation of this particular uh, increasing trend in the new CC frequency, where this particular CC bond uh, wave number is much higher over this to this. So now this is the last part of our lecture, that why some IR peaks are sharp and some are broad. So basically sharp peaks are actually because of the strong and isolated bond. Also, that the clear and well-defined dipole moment change also show as a prominent reason of getting the sharp peaks. And if the molecule is symmetric, then also we got the sharp peak. And the broad peaks is observed when there is a weaker bond is there, or the particular bond is influenced by the hydrogen bonding with the solvent. For example, that OH in alcohols, NH in amines, they are prone to do hydrogen bonding with the solvents, and which leads to the broad peaks. Also, there is a certain environmental, molecular environmental interaction is also there, and this actually varies the bond strengths, and which actually shows responsible for the broad peaks. Also, if the molecule is so much complex or a asymmetric molecular environment is there, and also there is a bulkier group is also there, for that particular case also we observe the broad peaks. So with this, we have to end our IR spectroscopy course. So I believe that whatever the last 6 lecture is enough for your exam purpose. However, if you want to learn more, then you can follow some books and all. But for the exam purpose, I believe that this will be enough. So with this, we have to end this particular class as well as the course. So in the next part, we are talking about the NMR spectroscopy. So thank you for listening, and do solve the questions and solve the community tab questions also. So thank you for listening.